All right, today we're going to look at the kinematic equations and how we can use them to solve typical physics problems. If we're going to start with a kinematics problem, probably the number one thing we want to do, draw a picture. We want to read the problem, we want to see what's going on. And if you can draw a picture, you could probably explain it better than any other way you can explain it. Then you look at what you know and what you don't know, givens, and also inferences that you can make based on what you know from the problem. Then you need to identify unknowns, what you're solving for. Then look for an equation. And sometimes you'll need more than one equation, depending on what the problem's asking you to do. But you'll have a list of equations in front of you, and you just have to figure out what equation works with what you know and don't know. Substitute into the equation, right? Make sure units match, and then come up with a solution. And then lastly, check. Does it make sense? Sometimes you'll get a number and you're like, that makes no sense whatsoever, and the number one thing could be units. All right? Remember, meters, seconds, very important in kinematics, and then when we get into dynamics, kilograms are going to be very important when we talk about mass. But we want to make sure meters and seconds are what we're getting to when we're talking about kinematics. So here's the first equation. And this is x, which is your final position. That's equal to your initial or starting position. You also, if you want to go xi, you can do that. You take your average velocity, all right, average, which is total displacement over total time, and then multiply it by time. And that will give you a final position. Now, we're assuming that acceleration is constant using this equation. So here's an example. A jogger runs down a straight stretch of road with an average velocity of 4 meters per second for 2 minutes. What is his final position, taking his initial position to be 0? So here's our jogger, and he's running this way. Okay, there's my picture, nothing fancy. I know this, right, is average velocity. I know my 2 minutes is time. And I know my initial positions to be 0. And I'm trying to find my final position. So obviously the equation we want to use is the one we just previously mentioned. X initial plus average velocity times time. And now I just substitute. I'm solving for final position. My initial position is 0. I add to that my velocity, which is 4 meters per second. Now my time, and here's where units come into play. Meters per second. That means I want to convert 2 minutes into seconds, which we know to be 120. So I got 120 seconds times 4 meters per second plus 0. So this is 4 times 120. 480 meters. And that is my final position. So that's the first equation going through the steps. Here's our next equation, and this one comes up quite a bit. This is where we look at a change in velocity, where we have a final velocity is equal to our initial velocity. Again, if you want to go VI when you write it, that's fine. Plus our acceleration multiplied by time. So V equals, or VF, if you want to say final velocity, is equal to initial velocity plus acceleration times time. So we have an airplane landing with an initial velocity of 70 meters per second and then decelerates at 1.50 meters per second squared for 40 seconds. What is its final velocity? So we got the airplane coming in, and this is my airplane, and it lands, right? We'll say it's landing, I guess, because it's going to decelerate. But what is its final velocity? All right, so we know that it lands with a 70 meters per second. So this is going to be our initial velocity. Our acceleration is meters per second squared units, so we know it's going to be 1.50. And we know, so this is going to be our A. And then we know 40 seconds is our time. We're in meters and seconds, so everything's good. We don't have to do any any kind of work with the units. But look at this, decelerates. So we're slowing down. So if we assume that we're going positive 70 meters per second and we're slowing down, our acceleration is going to have to be a negative number. So negative 1.50. And now we want to solve for final velocity is equal to initial velocity plus acceleration times time. So v is equal to 70 plus negative 1.50 times time of 40 seconds. And our final velocity will be, and we'll do the math, and I see that I got 70 minus, because that's a negative sign, 60 is equal to my final velocity, which turns out to be 10 meters per second. And once again, since I know I got meters per second and seconds and meters per second squared, and I have everything in meters and seconds, I know the units of my velocity will be in meters per second. That's why it's important that you do that. So my final velocity would be 10 meters per second. Now, probably the equation that gets people the most worked up is this one. It's equation 3. Final position is equal to where you start, your initial position, plus your initial velocity times time, plus 1/2 times your acceleration times your time squared. This equation is an interesting equation. A lot of stuff here, okay? But this is one that you're going to use a lot. Don't be afraid of this quadratic-looking equation. A lot of times we can use zeros, and if we can get zeros in there, it makes the math a lot easier. So, talking about dragster. A dragster can achieve average accelerations of 26 meters per second squared. Suppose such a dragster accelerates from rest at this rate for 5.56 seconds. How far does it travel in this time? So, going back, here's what I got. I have an acceleration, right? So there's my A, is 26.0 meters per second squared. All right? Accelerates from rest. Rest means you're not moving, right? You're at rest. So my initial velocity is 0. And then I see my time, 5.56 seconds. Again, let's look. I got meters per second squared. I got seconds. I have everything the way I want, and this 0 can be any units I want it to be, so I'm going to say it's meters per second. Again, just to keep my meters and seconds going. How far does it travel in this time? How far, right, equals where I start, plus initial velocity times time, plus 1/2 a t squared. Now I substitute. I'm solving for x. Since our dragster, and we'll draw the picture late, but our dragster starts here and travels to here, I'm going to say my starting point is 0 plus my initial velocity of 0 times my time of 5.56 plus 1/2, 26 is my acceleration, and my time is 5.56 squared. This is 0, this is 0. So essentially, my x is going to be equal to just 1/2 times 26 times 5.56 all squared. So I punch all this in my calculator, and I get 401.87 Looks like 3 sig figs here, 3 sig figs here, so I'm just going to say 402 meters. And again, I know it's meters because I already made sure that I kept everything in meters and seconds. Keep doing that and your units will become easy. Last equation, and this one has squares, but I like this equation a lot. My final velocity squared is equal to my initial velocity squared plus 2 times my acceleration multiplied by final position, right, minus initial position. So that's my distance traveled, essentially, okay? Now, the squares, again, it turns into an algebra problem, so don't get caught up on squares. So we want to find the final velocity of the dragster, okay? without using information about time. Dragsters can achieve average accelerations of 26 meters per second squared. So we want to find final velocity without knowing about time. Our distance in this case we've solved for is 402 meters, okay? So we're going to say v squared, or v final squared, is equal to v0 squared plus 2 times my acceleration, final position minus initial position. So think about what's going on. Again, our dragster is here. It starts at rest. So if it's at rest, my initial velocity is 0. My initial position is also 0, okay? And that's because I'm starting at this point and I know my final position is 402 meters. That's what I calculated before. So now I'm going to substitute in. So I got v squared is equal to 0 squared plus 2 times 26. I take 402 minus 0. And now, as I do the math, that's going to be gone. I solve this, but then to get rid of the v squared, I have to take a square root. So my v turns out to be, the answer should come out to be 145. And since I'm still in meters per second, meters per seconds should be meters per second. So we said 145, right? And we know now what our final velocity is of our dragster, okay, without worrying about time. So we could use that same equation using information from before. Before I finish, I just want to go back and point a couple things out about these equations as you write them down. A couple things. Equation 1, remember, acceleration is constant, so there's no acceleration, okay? Equation 2, if you look closely, okay, in equation 2, there's no distance, all right? So there's no distance involved in equation 2. There's no x, okay? In equation, in equation 2, my bad, no x. Now, in equation 3, if you look closely, there's no final velocity, so there's no v, all right? No final velocity known. And in equation 4, as we just saw, there's no time. Knowing this also helps us when it comes to making predictions about which equation to use. So, using these equations, work through problems, draw pictures, write down what you know, substitute, and then solve for the unknown. Good luck.